So after the last class, do you have any doubt? Anyone? Just let me know.
No, sir.
Okay, so all the things are clear, right? Okay, so what we discussed in the last class, we have discussed about all those like what is link, what are the different types of links. There we have seen that basically links is uh, kind of the buildings of product mechanism. Similarly, the types of links based on like whether they are rigid, flexible, fluid kind of link, or similarly based on their you can say how many other uh, like other kind of link can be joined to its or joined to its end. Okay, based on that we have got all different types of links like binary links. We have got ternary, have got quaternary, etc. That is depending on how many other links that I can. Okay, so there also we have said that is my screen visible?
Yes, sir.
Yes, sir.
Okay, okay, thank you. So there we have seen that basically here for this case for this particular link. So these are like 3 points where I can three ends where revolute or turning pairs can place. So it becomes a kind of ternary link. Okay, and to show that this is a single link, not a kind of three different binary links, we draw it like with this kind of hatch mark. Okay, so those things already we have discussed. Then we have also discussed about pair, the different types of pairs. We have discussed the slider crank mechanism in details. Do you remember about slider crank mechanism? How many links were there?
Four, sir.
Four links. What are they?
The frame, crank, connecting rod, and slider.
Okay, so what kind of movement they have? The crank, what kind of motion? Can rotate, right? Then the connecting rod and the crank, what kind of pair they constitute based on the type of movement? So based on that, we have seen that it's making revolute or turning pair. Okay, so the we have discussed the different classification of pairs, which may be based on contact. Under based on contact, we have seen lower pair and higher pair. So lower pair means what kind of contact between the surfaces, line or point contact or area of what type. Lower pair. It's area or surface type of contact. Okay, like the pin joint. Okay, so pin joint is restricted to lower. Okay, because two of the pins have got directly have got the contact to the surface, so that it shows to either area contact or surface contact. Similarly, higher pair, it's kind of either line contact or point contact. Okay, so between the members which are there. Okay, so that we have discussed. Similarly, types of concept based on type of concept, we have post pair based on the type of static pair, running pair, etc. So those things are we have discussed in details. If you have any other question, you can. Otherwise, we'll move to the next topic, that is our kinematic chain. Anyone may respond so that whether I should move ahead. Okay, I'm assuming you have understood. So next topic is basically
Yes,
about
sir.
kinematic chain. So what do you understand by kinematic chain? Okay, and sometimes only if we write chain, then also we mean kinematic chain only. So if you want to define it, so we can define it as a kind of assembly of links, okay, in which the relative motion between the links is possible. It will be there, but and the motion of each relative to the other one is defined. Okay, that means it's a kind of
None
completely
of which
constant
is
motion.
in.
Yes, is it clear now? So it's the
Yes, sir.
completely constant motion that we are talking about. For others, is my voice okay?
Oh, now it's okay, sir.
Sometimes breaking, sir.
Okay.
It's
So now,
badly breaking.
Cannot hear the words properly, sir.
is it okay now? Hello.
Can you speak again, sir? Oh,
Yes.
yes,
Is
sir. Yes, now
is
it's
it is it
working.
Sir, now it's okay, sir.
okay? It's okay, right? Okay. Okay, thank you. So
Actually,
now,
sometimes it's breaking and
sometimes it. Okay. So now we are that is about kinematic chain. Now there is something called as like redundant chain. So the word redundant, it actually means that it is not allowing any kind of motion of a link relative to the other. For example, if you consider suppose a link is something like this, okay, and suppose this was the link, okay, and to the end we already know this is a kind of binary kind of link, okay, this thing if we consider, and now at this particular end let's consider we are having something like this and it is being welded there, okay. So ultimately what happens, there is no motion between them, it is possible, okay. So now in that kind of case, actually this chain is making redundant chain, okay. It has got no kind of, you can say, actual motion, or ultimately what was our intended person, it is not going to serve that, okay. The relative motion between them, it is not there, and it's not even completely constant kind of motion, okay. So there like if let's consider we are now one of the link of a redundant chain is now fixed. Okay, let's consider we are fixing this. We have already told that by this kind of marking we mean fixed link. So now if that is happening, then we actually get a kind of structure also known as a lock system. Okay, so that is about dynamic chain. Now we are saying that mostly we'll be dealing with lower pairs because most of the times we'll be talking about different mechanisms where the joint is kind of the pin joint. And whenever two links are being joined with pin joint, we know that if whatever pair they constitute, that is kind of the lower pair mechanism that we are talking about. Now we have seen that like we can have assembly of different links and it should fulfill certain criteria, then only we'll be calling it as a kind of kinematic chain, okay. Only just mere just connecting one link with other will not result into a kinematic chain. And if it has to be kinematic chain, with respect to lower pairs we have got two simple consider relationship, okay, whether between the link and the number of pairs whichever is there, and from that particular relationship whether they hold good or not, depending on that, if they hold good, actually we have got two equations, and if they hold good, then we will say that basically it is forming a kinematic chain. So later on also, whenever we will be solving certain problems, initially we have to check whether that particular assembly is a kinematic chain or not, then only we'll be able to go for the next higher derivative of it, like the about we'll be discussing about the mechanism, etc., etc. So now what is these two equations? Small is a very easy and small equation which is there for lower pairs to determine whether a assembly of links and pairs whether they are forming kinematic chain or not. So first one is L equal to, you may note it down, L equal to 2p minus 4. So here this L, it is nothing but L stands for the number of links. That means how many links are there, and P is nothing but the number of pairs. That means how many pairs are there in that particular assembly. That is one. So that means the left hand side, that is number of links, should be equal to 2p minus 4. Apart from that, another one is there, that is L equal to, you can note it down, that is important, L equal to 2 by 3 whole into say plus 2. Now here again, once again, L is the same thing, that is the number of links. Now this 2 by 3, these are 2 3, those are constant, nothing but constant, and L is the number of joints. So how many joints are there? Now if these two equations, equation 1 and equation 2, they are satisfied, then this assembly, okay, that assembly of links will form a kinematic chain. Okay, so this is very simple. So you just have to remember that check by simply putting the number of lanes, number of pairs, etc., and let's check whether it is making a kinematic chain or not. So for that, just taking a small example, and let's consider this is the situation, this triangle kind of thing, it is the situation. So we have got this ABC, okay. So here these are all binary or ternary, or what kind of link are there, link are these?
Binary, sir.
Binary.
These are three binary links. One, okay, this is one, and this and they are joined, okay, to second link, and this is the third link. Let's check whether this assembly of link and pair, they are actually forming any kinematic chain or not. So now here, what is the number of links? L is first, second link, this is third link. So L equal to what? 3, right? You are with me?
Yes, sir.
Okay. Now what is the number of pairs? That is P. So pair means how many links will be there in a pair to form a pair? Two links, it has to be joined together and having relative motion between them, right? So that is going to form a particular pair. So now if you consider 1 and 2, there is this particular joint. Okay, if you consider 2 and 3, there is this particular joint. So, and if you consider 3 and 1, there is this particular joint. That means how many joints?
3
J
joints.
equal to,
3, sir.
correct, J equal to 3. And now pair, how many pairs? So 1 and 2, it is forming one pair. Okay, so 1 and 2, so this is one pair. If you consider 2 and 3, they are also joined. So 2 and 3, that is forming another pair. And once again, 3 and 1, they are forming another pair. Okay, so P equal to 3. So now, if we write 1 and 2, or if you just inverse them, that is 2 and 1, they mean the same thing. Okay, it is not 2 and 1 that combination and 1 and 2 that combination, it is the same thing. Okay, so now I'll just put it on the equation, two equations that I have, that is L equal to 2P minus 4. So L equal to 3. So 2 into P equal to 3 minus 4 equal to 2. So 3 is 1. Is it possible 3 equal to 2? This is not true.
No, sir.
Correct. Similarly, if you put for like the second equation, once again, J is 2. So if you put then 3 equal to 10 by 3. Definitely not true. So this particular assembly is, this is a kinematic chain or not? So it is not fulfilling those criteria. So it is not a kinematic chain. Okay. So this is basically the structure. Similarly, simply if you just try, okay, you try for this. Okay, like this kind of situation. Okay, all of you just on your copy, you just do this. Check whether it is a kinematic chain or not. This assembly, this one, kind of rectangular thing. Similarly for a pentagon kind of thing. Okay, this is the second case. You do it. All of you individually, you just check. So this is the third case. Okay. So for this, what is the number? You have to check what is P, what is the number of links, what is the number of pairs, and what is the number of joints. First, you have to check the joints, the links. Sorry. So how many links are there? L equal to 1,
4,
2,
sir.
correct, 3, and 4. So 4 links. Now, how many pairs they are constituting?
4, sir.
So correct. 1 and 2, one pair. 2 and 3, another pair. 3 and 4, another pair. And 4 and 1, another pair. So how many pairs? 4. And it is very evident joint is also 4. So if you put them and check whether they are fulfilling the equations or not. So here in this case, both the equations will be fulfilled or not. Just check. It's a kinematic pair or not. And for both of them, I'm giving you 1 minute. Just check these two whether they are kinetic pair or not. Done. First one, the rectangular one, it's a kinematic pair, kinematic chain or not? Not pair, sorry.
Yes, sir.
Yes, correct.
Yes,
So
sir.
it is fulfilling both the equations. So it's a kinematic chain. Next one, you check. What is number of link here? How many links are there?
5, sir.
Yes, sir.
Pairs,
5, sir.
correct. correct. And joints.
5, sir, I think.
Yes, correct. So these are very basic thing actually. So from here later on there will be different type of things. Okay, there will be different mechanisms like different links etc. in a particular mechanism. So now just check whether they are fulfilling the equations or not.
Not kinematic, sir.
Okay, so they are not fulfilling the equation, so it's not a kinematic thing. Okay, so this way, whenever later on you have to check whether you have to go for suppose finding out the sometimes degree of freedom DOF. Okay, initially you have to check whether it's a kinematic chain or not. If it is not a kinematic chain, definitely it is not going to be a kind of mechanism. If not, it's not a mechanism. We are not going for discussing about the degree of freedom of it. Okay, so first thing it should be a kinematic chain. Okay, it should fulfill this equation. Okay, so up to this much, I hope everyone is clear. So same kind of thing if we extend to some other loop. Okay, so with the loop you should not get like if suppose the loop is something like this. Okay, later on you'll see there may be different configuration diagram for different mechanisms. Sometimes it may be bigger, it may be smaller, or like this, like that. Okay, so it might happen like this. Okay, you might have to sometimes check whether they are what kind of assembly they are having. Okay, so what does this positions represents? Whatever I am drawing right now. So they are what this way. If I draw this shows fixed positions. Okay, and all the fixed thing always be number with the same number. Okay, suppose if this is one, this is also one. This is the same link. We don't give three different link numbers to the fixed position. Understood? This is one of the rules you must remember. Okay. Then after that, this is another to this whole thing is as it is heads. This is another thing. This whole thing another link. Okay, because similarly here it is link 5 maybe. Okay, link 6, 7. This is 8. We have 9 like this. Okay, so this also you can check, and later on will be finding out suppose degree of freedom for this kind of situation also. Okay, this is known as what kind of diagram for the mechanism where we draw it with kind of line in a simpler manner known as the configuration diagram. Okay, also sometimes the kinematic diagram. Okay, so configuration diagram. So now next thing we must know about, now we know about link, we know about the next thing pair, we know about the next higher thing that is kinematic chain. Now we must know about mechanism. Now how we can define mechanism. So there are like one of I'm getting one. Okay, so mechanism. So already one definition of mechanism already we have discussed previously. So there is another definition of mechanism. Now how we can get a mechanism? Sometimes it's also asked. It's like when one of the link of a kinematic chain is fixed, then we get mechanism. So based on that, we can have like two types of mechanism. One is the simple mechanism. It has four links, and whenever it consists of more than four links, we call it as compound mechanism. Okay. So now we are saying that if we have got a kinematic chain and one of the link, only one, okay, only one of the link of a kinematic chain that is fixed, we get what? A mechanism out of it. Understood? Now let's consider we have got suppose this kind of kinematic chain which is known as the 4-bar chain. Okay, we have got four different links here. Okay, so now there is another concept which is known as inversion of mechanism. Now let's consider this figure. All of you can see. So how many links are here in this particular mechanism? Already we have studied whether this situation, this assembly is giving rise to mechanism or not, kinematic chain or not. It's giving rise to a kinematic chain, right? Hello.
Yes, sir.
Okay. So now we
Yes,
have
sir.
got how many links here? 4, right? Okay.
Okay.
So now we are saying that one of the link of the kinematic chain, if it is fixed, it gives rise to a what? Mechanism. Now it's possible that and that is one at a time. And now it's possible that I can fix one of the links by fixing different links. That is also possible. So this concept is basically the giving rise to the concept of inversion of mechanism. Now the process of obtaining different mechanism by fixing the different links of the same from the same kinematic chain, it is called the inversion of mechanism. Now we have got the same kinematic chain. This is the kinematic chain is fixed. Now if you fix link 1, then you are going to get a mechanism out of it. Let's consider only you are fixing link 2, then also you are going to get a different mechanism. Let's consider you are only fixing link 3, so that is there. So now if you are getting obtaining different the process of obtaining different mechanism by fixing the all different links of the same kinematic chain one at a time, that is known as the inversion of mechanism. Okay, and in this case the relative motion between the different links, it is not going to change, but the absolute motion will be changing. Okay, and whatever higher pair you have already studied, that is having line or point contact, they cannot be inverted. That is important. That's why inversion of mechanism mostly you will see for the lower pair mechanisms only. Okay, understood? So now if someone asks you, let's consider there is a kinematic chain having n number of links. Okay, n number of links. So how many inversions will be there? How many inversion of this particular kinematic chain? N number of links we have got for this kinematic chain. How many inversions? Anyone who can tell me? Fair Mickey?
N minus 1, sir.
N minus 1. Okay. Partha? Rehan, what do you think? So in the previous case, what you have seen? So we fix one link at a time. So if I have got n alternative, n links, so how many times I can fix one link at a time from n number of links? I can fix n times. So in general, n number of links, a kinematic chain having n number of links will give rise to n number of inversions. Understood? So now why this concept is important? See, there are some basic kinematic chain which are very important, like the 4-bar chain. Okay. Similarly, we have got the slider crank chain. We have also got double slider crank chain. Okay. So these are some of the 3 very important kinematic chain, and their inversion provide many useful mechanisms. So they are all lower pair mechanism. So if we are talking about 4-bar chain, okay, in simplest form, this is the 4-bar chain. We have got 4 different links joined by turning pair. Okay, so all are turning pairs only. So if I fix one of the link here, it gives rise to a kind of 4-bar chain. It's the simplest of all the mechanism, and here all are pin jointed, so all are turning pair. So already we have discussed about slider crank chain. So there we have seen 3 turning pairs and 1 number of sliding pair. Okay, so the frame and the slider, they are giving rise to sliding pair. Also we have got double slider crank chain, and fixing one link from the double slider crank chain will give rise to a mechanism. Okay, and how inversions also we can get by fixing different links. Okay, up to this much any confusion?
Yes, sir.
Okay, so now just like we have got binary link, ternary link, etc. Okay, then there are also different types of joints. So depending on how many, if you consider this particular case, okay, let's consider this is a kinematic chain, okay, or you can say right now I don't know whether it's a kinematic chain or not. We can verify always, okay, by checking the number of links, pairs and joints. We can verify whether it's going to form a kinematic chain or not. Right now let's consider it's a kind of assemblage of different links that is there. So now we have seen there are actually the whole all the type of links are what kind of links: binary, ternary, quaternary in this particular figure. Links, what about the links? These links are all binary links, right? Because it has got two ends where I can have other revolute joint, and I can revolute pair, I can join. Okay, so all are actually binary. But you can see at this is a joint, this is a joint, this is a joint, this is a joint. Okay, but you can see in these joints how many links are actually joined. So here in this case, if you check, then we have got this link and this link, they are joined here. So two numbers of link whenever joined at the same connection, it is this joint is known as binary joint. Now let's consider this case. Now you can see link 1, link 2 and link 3, they are joined at this particular zone, okay, single connection. So three numbers are there, so it is ternary type of joint. Similarly, if you look at this, okay, we have got four different links which are connected here, so it will be quaternary joint like that. Okay, so similarly we can go for other higher members. Okay, so this is about it. Now one thing that you must know is, so whatever all those normal link etc, normal join etc that we are talking about, okay, so those pairs that we are talking about, okay, so actually we'll whenever this binary kind of joint and ultimately one single pair that is there, okay, if this is a binary joint, that means two links are joined here, okay, so it gives rise to how many pairs? This binary joint, how many pairs are there? One pair, correct, correct. Okay,
One
so
pair, sir.
correct. Let's consider now it has become a ternary joint. That means three links are there. How many pairs are here?
3, sir.
Hmm?
Three, sir.
Okay. Now let's consider if we ask you like this. So this is equivalent to how many binary joints? So I can consider it to be equivalent to two binary joints. Okay, so ultimately two binary joint means two pairs. So this ternary link or quaternary etc, if you go for, in general that means what happens, if there are n number of links are connected at a joint, okay, it is equivalent to n minus 1 binary joints. Understood? That means 3, that is ternary joint, equivalent to 2 binary joints, 3 minus 1. Quaternary joints equivalent to 3 binary joints similarly. Okay, understood? That is the concept that will be required. Understood?
Yes.
Okay, now if you consider this particular case, okay, now this join A, if you look at, so how many links are joined here? How many links are joined here? There is link 3, link 4 and link 5. 3 numbers of links are joined here. So A is a what kind of join? Binary, ternary, quaternary?
Ternary.
Ternary. Okay, okay, so if it is a ternary join, it is equivalent to how many binary joins, and ultimately how many pairs? That means
2.
2, correct. So that is the thing. Okay, so why this concept is important? Because later on whenever we will be discussing about, we'll be finding out the degree of freedom of mechanism, then this is the easiest way to do it, easiest way to find out. So by looking at the type of things, okay, so if it is kind of like, because see, if it is simple kind of mechanism, you can always keep on counting. Suppose if this is the case, simple four-bar mechanism. Okay, you can always keep on counting. Suppose how many pairs are there. But if the complexity level goes increasing like this, maybe some others or like that. Okay, so in that case, you will get confused. Okay, here it is very easy. 1, 2, 3, 4, 4 links are here. Okay, so you may count like 1 and 2 is one link, one pair, 2 and 3 another pair, then 3 and 4 another pair, and 1 and 4 another pair. You will be counting like this. Yes, 4 pairs. But if the complexity increases, you will get puzzle. That's why by looking at the type of joints, we'll be checking how many types of how many numbers of joints are there, how many what kind of type, okay, whether it's binary, ternary, or like that. And the higher level of joint, that means ternary, quaternary, etc., will decrease it to like equivalent binary, and from there we'll automatically get the type of, you can say, whatever is the type of number of pairs that is available. Okay, after this was any confusion? Is it okay? Is it clear?
Yes, sir.
Okay. So now we'll be discussing about the types of constraint motion. So constraint, by the word constraint, what we know, we have already said that it's a kind of, the movement is kind of limited, or you can say kind of predictable. So there are three types of constraint movement. One is known as the completely constrained motion, another is known as incompletely constrained motion, and one is successfully complete constrained motion. So how we can define completely constrained motion? So here in this particular case, the motion between two elements of a pair, it will be in a definite direction irrespective of the direction of the force applied. That means let's consider this case. Okay, case of inserting a square bar inside the square hole. So in this case, if you are inserting, if you're inserting this particular square bar inside the square hole, irrespective of how basically uh, you are applying the force, whether you are applying like this or exactly horizontal or like this, because of this particular square guide, actually it will be moving in this direction only. So this is completely constant motion. Okay, similarly there is incomplete constant motion that is there. So here that means the motion is possible in more than one direction, but how you are applying the force, based on that you are going to get the motion. So that means you can consider a circular bar which is moving in a circular hole. It can be rotating motion also, it might be there, because it can rotate it. Also directly reciprocating motion, to and fro kind of motion also you can have within that hole. Okay, so and both the motions are independent of each other. So this kind of motion, okay, depending on whether you are rotating it, if you rotate it, it will have the rotational motion and you will get inserted. If you just push it, okay, you'll sliding, you'll just reciprocate and go inside. So both the motions are possible, but how you are applying the force, it is based on that. So that kind of situation is incompletely constant motion. And we have got successfully constant motion, where it is possible to have more than one motion, but one of the motion we are going to completely eliminate. Okay, so some external means will be there. So that kind of motion between two elements of it is possible in more than one direction, but it is made to have motion only in one direction, which is not completed by itself, but some other external means it. Okay, so that kind of consideration will be falling as successfully constant motion. We can consider the example of the motion of a piston which is there inside the cylinder. So it is not due to the motion is, it's not happening by itself, but it is due to the rotation of the crank. And that crank, it has only got, like you can say, and it has only reciprocal motion and no rotational motion due to the constraint. Okay, the piston we are talking about. Okay, and it is happening because where the crank is rotating. Okay, so that is the thing. Similarly, IC engine valve, if you consider, so they will not have their own movement, but there is something called as rocker arm which is going to give the movement to it. Okay, so these are the three types of constraint type of motion. Okay, understood? Is it clear? Okay then, so if everything is clear, so for today we'll stop here. I'll be taking your attendance, just respond to your main calls. Okay, Nilutpal, absent. Shankar, Shankar, absent. Rasisman,
Present, sir.
Rehan,
Present, sir.
Partha, Partha,
Present, sir.
Rishikesh Basumatari, Rishikesh Basumatari,
Present, sir.
Hermiki,
Panza,
Nahosol,
Present, sir.
Teza, Teza,
present, sir.
Rishikesh Nath, Rishikesh Nath, absent.
Yes, sir.
And Emil.
Yes, sir.
Okay, so with this we'll stop this one. Okay, thank you everyone for joining.
Yes, sir. Thank you, sir.
Thank you, sir.
Present, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.